So in this question, we are looking at a DC chopper that has an inductive load with a battery attached on each side, and then this chopper being supplied with a voltage at a given frequency. Then its duty cycle is also provided. So the question says the DC chopper has an inductive load of R is equal to 10 ohms. Then inductance L is equal to 20 millihenries. The input voltage value is Vs is equal to 220 volts. Frequency is 5 kilohertz. Then the E of the battery attached on the load side is 100 volts. And duty cycle K is 0.5. Calculate the average load current, RMS load current, RMS value of the chopper current, the effective input resistance, and we shall draw the voltage across the diode. So this is the circuit, and this is the power BJT or the power transistor. This is the freewheeling diode. This is the inductance or the inductor. This is the load resistance, and this is the battery. So right away, let's begin. First of all, we have already identified that this is an RLE load, and therefore the average load current is going to be V0 minus E divided by the load resistance. But V0 is the same as duty cycle times Vs, which is the same as KVS. So the average load current is therefore going to be KVS minus E divided by RL. So this is going to be K is 0.5, Vs is 220, E is 100, R is 10. So this is going to be 110 minus 100 divided by 10, giving us 1 amp. So the average load current is going to be 1 ampere. Then let's look at I naught, the RMS load current. So I naught, or the IRMS of the load. So this is given by, first of all, we know it is going to be of different values. So we have when the chopper is off, when at time t equal to t off, then what is going to happen is that I naught, the RMS value of this load current, is going to be given by negative E out of R into 1 minus exponential of negative t divided by tau, which is the time constant, then plus I mean exponential of negative t divided by tau. So we know E, we know R, we know T off, we can get it. So we know that obviously the frequency is equal to 5 kilohertz. So meaning 1 out of T is equal to 5 kilohertz, meaning that T, which is the time period for this cycle, is going to be 1 out of 5 times 10 power negative 3, and this is giving us 0.1 divided by 5 is 0.2. So this is 0.2 times 10 power negative 3 seconds. So what does that tell us? We need also to get T on. So T on is equal to alpha T. Alpha is 0.5 times 0.2 times 10 power negative 3, and this is 0.1 times 10 power negative 3 seconds. T off therefore can also be T minus T on, and this is 0.2 times 10 power negative 3 minus 0.1 times 10 power negative 3, and this is giving us 0.1 times 10 power negative 3 seconds. So that is the time off, or the off time of the chopper circuit. So what is this going to tell us? So we can get the I naught RMS. Why do we need to get the I naught RMS when the chopper is off? Because when the chopper is off, the freewheeling diode provides a path for any current that was flowing by the time the chopper was put off. So that current will help us to be discharged to the load at steady state or steadily without affecting our circuit. So for that matter, we need to get the I not RMS value when the chopper is off to get that current that is going to be flowing through the diode or the freewheeling diode when the chopper is off. So this is going to be negative 100 divided by 10 into 1 minus e exponential of negative 0.1 times 10 power negative 3 divided by 0. 0 point what? We need to get tau. So this is tau. So we need to get tau. So tau, which is the time constant. So we need to also add I mean, then negative t divided by tau. So what is tau? Since this is an error or RL circuit or RL rod, then we shall define our time constant from L divided by R, and this is 20 times 10 power negative 3 divided by 10. This is giving us 2 times 10 power negative 3 seconds. So that is the time that it takes for the inductor to have its current rise or fall to 0.632 of the maximum or of the minimum value. So now what do we remain with here? So we just substitute in our values. So when we substitute in, we need also get the I mean. So the I naught mean, which is now always given by Vs divided by R into E, T on divided by tau minus 1 divided by E, then time period divided by tau minus 1, then minus E out of R. So this is going to be 220 divided by R, which is 10, into exponential of T on, which is 0.1 times 10 power negative 3 divided by tau, which is 0. It is actually 2 times 10 power negative 3 minus 1 divided by exponential of period. The period given to us, or which has been calculated, is 0.2 times 10 power negative 3 divided by 2, then minus 1, then minus 100 divided by 10. So this value is going to be, 22 into 0.0512 divided by 0.105 minus 10, and this is giving us 0.7276 amps. So meaning the I naught RMS when the chopper is off is going to be negative what? Negative 100 divided by 10 into 1 minus exponential of negative 0.1 times 10 power negative 3 divided by 2 times 10 power negative 3. Then we are going to add 0.7276 times exponential of negative 0.1 times 10 power negative 3 divided by 2 times 10 power negative 3. So what is this value going to be? I naught RMS when the chopper is off This is going to give us negative 0.4877 plus 0.7276 times 0.95123. And this is equal to 0.2 amps. So when the chopper is off, the freewheeling diode will conduct a current equivalent to 0.2 amps. Now, when the chopper is on, so when the chopper is on, so at T is equal to T on, and this is 0.1 times 10 power negative 3 seconds. So now, the formula for I not RMS when the chopper is on is going to be Vs minus E divided by R into 1 minus exponential of 0.1 divided by 2. Yes. Then we are adding 0.7276 times exponential of negative 0.1 divided by 2. So we know this Vs as 220 minus 10 minus 100 divided by 10, and we are multiplying it by that value, 1 minus exponential negative 0.1 divided by 2 plus 0.7276 times exponential of negative 0.05. Finally, this value is going to be, 0.0585 plus 0.6921. And this is going to give us 1.277 amps. So that is the root mean square value when the chopper is on. Then let's look for the RMS value of the chopper current. So RMS value of chopper current, so that IR is going to be square root of the duty cycle multiplied by the I average. So this is going to be root of alpha I average. And this is square root of 0.5. We multiply it by 1. This is 0.707. Then next is to get the effective input resistance. Effective input resistance, Ri. This is equivalent to RL divided by K, or divided by alpha, or divided by duty cycle. This is 10 divided by 0.5, and this is 20 ohms. Then lastly is to get the voltage across the diode. So when the diode is conducting, voltage drop across it is going to be 0. So when t or time is equal to T off time of the chopper, then Vd is equal to 0. Diode is conducting. Then when T or time is equal to T on, Vd is equal to Vs. That is when the diode is not conducting, and the voltage supply appears across the diode because they are always in parallel. So for that matter, therefore, if you draw the circuit, for example, you have the DC voltage source, this is the switch, and this is the freewheeling diode. You have the inductor, maybe you have the capacitor here, then finally you have a load this side. This is E, this is R, this is L, this is C, this is the freewheeling diode. So the voltage across here is the same as the voltage across the diode because they are in parallel. So what does that mean? To draw the voltage curve, I will say this is Vs and this is time. The voltage supply is a constant. Then we have to also look at the diode conducting and when the diode is not conducting. So this is Vd, this is time. So here is T, this is T on, and this is T off. So that is how we can get the diode circuit and the voltages across the diode.